Guy. Good morning.
Hey, how's it going?
Good.
I'm doing really well, actually. It is indeed morning for me, and not too terribly early, just 9 a.m. So,
9 a.m. Yeah. But still, thank you for connecting on this Saturday morning. Yeah, you were also one of the speakers who joined online speakers party yesterday. So how was it?
it's been good. It's been really good.
Okay, that's great. So what topic have you prepared for our participants today?
Well, I like to do talks with fun themes, and and I have things that I think are kind of fun. And one of the things I really enjoy, not necessarily as a believer, but as just because they're fun, is I enjoy UFOs. And so today I've got a UFO themed talk on probabilistic data structures, entitled "Understanding Probabilistic Data Structures with 112,092 UFO Sightings,"
Yeah, that
which is
sounds
kind of
really,
fun,
really
absurd, and
funny.
ridiculous.
Yeah. Okay, so please, if you are ready, start your presentation.
Sure, absolutely. Welcome everyone. I hope you're having a good Saturday afternoon in Kyiv. It is cold and morning here in Columbus, Ohio, where I'm coming from. And this is my talk, Understanding Probabilistic Data Structures with 112,092 UFO Sightings. My name is Guy Royse. I'm a developer advocate at Redis. There's really three things on this slide that matter to, well, sorted parties. There's the thing that matters to you, and there's the thing that matters to me, and there's the thing that matters to my boss. The thing that matters to my boss is that Redis logo right there. He wants you to know, and I want you to know, honestly, that Redis is a thing. We are more than just a cache. Go check out our stuff. I'm going to talk about some of the stuff that we can do with Redis that's more than a cache today, namely probabilistic data structures. And so, go check it out. I'm with Redis. Slides successfully branded. The thing that I care about is that little Twitter ID right there. So if you're not following me on Twitter, give me a follow. It helps me with my sense of self-worth. If my numbers get too low, I feel like I'm a failure in life. And if they're high, then I can just feel normal. So help me out there. And then there's the thing that you care about here, which is that github.com/Guy Royse. You can go out if you are curious about these probabilistic structures. I've got all the sample code that I'm going to use in my demos and my talks. I've got a bunch of probabilistic data structures that I've implemented in various programming languages, Java, C#, JavaScript. So you can go check out that code there, and there'll be a link to the specific repo at the end of the talk. And don't worry about that guide.dev link. That takes you to a blog that I haven't updated in over a year. So yeah, 112,092. This is an oddly specific number, and that's part of the, but it's also the number of UFO sightings in the National UFO Reporting Center's database, the NUFORC. They have cataloged over since the 50s, I think. Not the organization, but UFO sightings going back to the 50s in the United States. And so that's a lot of UFO sightings, over a course of, say, about 70 years. That's more than a year easily. It's a lot of UFO sightings. The data itself uses examples to, I'm going to use as an example to teach you about probabilistic data structures, but the data is absolutely delightful. And here's a little summary of what our data that we're going to play with looks like. You get, it's just a big CSV file with various fields in it. There's a summary, which is sort of it's a summary of the UFO sighting. So here, three saucer-shaped ships, three saucer-shaped ships, easy for me to say, high in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Yep, sounds like a UFO. It's got the city and state where near that sighting. So this happened near Salem, Oregon. It's got the date and time here, and so here we've got it's September the 15th of 1950. Nice ISO 8601 format on the date time. We've got the shape of the UFO, like disc or triangle. This one is a disc. Get the duration of that sighting. This is for humans to read, not for computers to read. So it's listing 15 minutes. It might say a couple of hours or a few seconds. Got the link to the NUFORC's web report, so you can go out and take a look at that link and view this UFO sighting online yourself. The full text to play with at the end, and then the latitude and longitude of that UFO sighting. of the city nearest to that UFO sighting. And this data exists in a format that I can use thanks to not only to Newfork, but to this wonderful man by the name of Tim Renner, who screen scraped the Newfork site to create a CSV file that he hosts on data.world. And he used it to do machine learning. He did a lot of really fun things. Like he wanted to plot out, where do UFO sightings tend to happen. And he found out that you plot them all out, that most of them happen within, 100 kilometers of a U.S. airbase. Not saying it was aliens, but it was the Air Force. He also did a plot to see what day of the year had the most UFO sightings. And it turns out the most common day of the year for a UFO sighting is on the 4th of July in the United States, which is our Independence Day, which is, the day we launch lots of fireworks. And so I just have this image in my head of this father and a son out there watching fireworks, and it's like, Dad, what's that? Is that a firework? It's like, no, son, that's a UFO. It's definitely not a firework. It's funny, actually. If you look at the charts, it's like an order of magnitude more sightings on the 4th of July than any other day of the year. I guess if I was an alien UFO wanting to come to the visit the United States, I would do it on the 4th of July because everyone would just assume that I was a firework. So anyhow, fun data. We're going to look at them and understand probabilistic data structures. So first question, probably that a lot of you have is, what the heck's a probabilistic data structure? This is actually a question I had years ago when I started looking into this topic. And when I started putting together this talk, I did a survey. How many of you have heard of probabilistic data structures? A very, very scientific survey on Twitter here. And, with 119 votes in my survey here, surely this is the absolute truth. And 58% of people who follow me that answered the poll had never heard of probabilistic data structures. And so if you haven't heard of probabilistic data structures, you're in good company. About a fifth of them had heard the term. These are developing to here too. So they probably said, yeah, I've heard of the term probabilistic data structures. It was in the question. So we're into this 80% of people really don't know anything about this topic. And then the other 20% either knew what they were or had actually used them. And they were split about 50-50. So if you don't know what a probabilistic data structure is, you're exactly who I want to talk to. So that is not surprising. It's perfectly normal. So in order to understand what a probabilistic data structure is, we need to compare them to their sort of opposite, the deterministic data structure. And you know what a deterministic data structure is, although you might not know you would want to call them that. These are the data structures that we use all the time in our programming. They're the lists and the sets and the hash tables and the queues and the graphs and all those data structures that we pick for a lot of different reasons. Usually because they reflect how our data itself is going to be represented. So we tend to use lists and arrays because we have a sequence of data. We'll use a table because we have, more of a key value sort of thing we want, or maybe we'll have a because, we want to process something. It is, these are the data structures that we have. You've used them. They're called deterministic because they do what you expect. Deterministic data structure, if you put something in it, it's going to be there when you ask it to back out. There's not any chance that it'll go away. They're deterministic. They do exactly what you think they'll do. The most popular version of a deterministic data structure that you've used, and I'm going to talk about how this works because the concepts in it are relevant to a lot of probabilistic data structures, and that is the hash table. And hash table, sorry, I'm moving my screen here so I can see any questions. So if you have any questions and you're online, feel free to drop them in chat, and I'll try and keep my eyes on chat and answer them during the talk. It's kind of like live streaming. But a hash table is your classic key value pair data structure. It's a dictionary. It's a hash map. It's I think in Ruby they call them hashes, where you provided a key like city, and then you can set the value to Salem, or you can get the value using that key. It's a key value store. Internally, hash tables make use of hashing functions. And a hashing function is can be thought of as compressing your data down to a single value. So here we've got some bytes coming in, and we've got a seed, and those two values together, when operated against a hashing function, will compress that down and create a unique signature, a thumbprint representing that that value. And it's one way, right? So if I given this data and this seed, I will deterministically get this number, say maybe like a 32-bit number. But I can't turn that 32-bit number back into the data. And this allows us to take any size data and squish it down to a signature or a finger. This could be a 2 GB document. This could be, the 6 bytes here that is the word Scully, UTF-8 encoded. And so that's what hashing functions do. You might be thinking cryptographic hashing, like SHA-256. You could build a hash table using those, but you probably wouldn't want to, because those particular hashing functions are optimized for security as opposed to performance. We're not really worried about being able to reverse engineer what the data that generated the hash was. We're worried about making a hash key, a hash that's fast, because we want our data structures to be fast. And so what a hash table does is it's an array of buckets. And when you first create that hash table, it's got a particular size, and it can be resized as time goes on, which is kind of slow. But the key idea behind it is when I want to shove something into the hash table, I take the key I want for the value that I want to shove it in. So we're going to store the city, and with the value of Salem. We take that city string, we run it through our hashing function with our seed, and then we modulate the width of our array. And that will give us an index between 0 and the length of that array minus 1. And so city is going to give some number, modulus of 10, and it says, hey, well, that's that index number 1 here. And so we take the value that we want to store in city, and we shove it into position 1. You put it in that bucket. And then when we go to add something else, say state, we hash state, we get a 32-bit number, a nice big number. We modulus it with 10 with the size of our hash table, and we get another index, and then we shove Oregon into the index there. Of course, we can have a lot of keys, and we only have 10 entries, and so a collision is unavoidable. And in the event of a collision, we append it to the end. So this bucket here, I really didn't say what the bucket was, and that was sort of on purpose. The bucket isn't just a string. It's just not just a value. It's a linked list. So what we're storing in that bucket is a linked list containing the value and either the key or the hash of the key. So when we hash the word shape, and we get a 1 here, then we go and say, hey, this bucket already has something in it, and it's not us. Append to that linked list. So it walks that linked list and says, does this match my hash? Does this match my hash? And if it doesn't, then we get to the end, then we tack it onto the end. And if it does, then we update the value. It's in the same index, it gets tacked to the list. It is reversing this process. So if we want to go look for city, then we again hash the value of city, get the index, and start walking that linked list until we get a matched hash. And if we find it, then we return it. And if we don't, then we would return null or nil. And so that's how a hash table works in 3 minutes. And so we choose a hash table versus, say, a linked list because we're making trade-offs, both in capability, but often in terms of time and space complexity. So some data structures are very performant, so they're time efficient, and some data structures are more space efficient, and we're trading off between these. So we would pick a hash table. Hash tables are fast. Accessing any particular key in a hash table is an O of 1 operation. So it takes the same amount of time regardless of how big your hash table is. But they can have they can be a little space inefficient because that array may have indices that aren't populated, but they're still taking up space in memory. Whereas a linked list is very efficient. It takes up exactly the amount of space it needs to, and no more and no less. However, trying to find something in a linked list requires traversing it. And so it becomes an O of n operation because you have to walk down that list. And so we choose our data structures because we're making these sorts of trade-offs. Do we need to be more performant? Do we need to be more compact? And actually, we're not even necessarily making a trade-off per se. It's a little bit of a lie there because there's also sort of a general capability. If we wanted something that was very fast and very space efficient, we can use arrays, right? But arrays are hard; they don't resize easily, so they have some capabilities that we're trading off in as well. Linked lists are actually really efficient to modify; they're just slow to traverse. And so it's not just a simple, linked list fast or slow, hash table fast. It's more nuanced than that. And actually, another thing, in addition to time and space complexity, that we can trade off against, and that's accuracy. We can choose to create data structures that are less accurate, that say are very fast and are very compact, but are only correct in, say, 98% of the time. And you might be thinking, why the heck would I want a data structure that lies to me? I want to put data in here and I want to get the right answer every time, always. I mean, these are computers. That's why we use them, because we want things to be accurate. Well, yes and no. See, when you start scaling your data up, the time and space complexity gets out of control. You've got, let's say, Facebook or Google, and you've got billions of users, and someone wants to create a new username. You can't just go out and do a select star from users where username equals with a billion rows. That's just does not scale, right? But a probabilistic data structure, which sacrifices accuracy, and says, well, let's see if this username's taken or not. And if it's correct 98% of the time, then that might be okay. If you've got a lot of data, that a little bit of accuracy is a reasonable trade-off. Because, hey, if I can drop the performance by an order of magnitude and only be wrong, a 0.1% of the time, that's totally worth it. So that's the idea behind a probabilistic data structure. And you've used things like this before. Sort of a good analogy is this picture of the Devil's Tower in the Badlands in Wyoming, made famous by Richard Dreyfuss and his mashed potatoes. That's a Close Encounters of the Third Kind reference for those who are not old like I am. So this picture of the Devil's Tower is presumably it's in PowerPoint, so it's probably not a JPEG anymore. But this particular pixel right here that I'm pointing out with my cursor, that blue one right there, the one that I keep circling. Yeah, we'll pretend I'm actually circling it. Okay. Is that better? That's okay. Sorry about that, everyone. The internet is hard. So this little blue pixel right it's not the right color, right? It's probably a shade of blue that's all this. But it doesn't matter, right? That JPEG lossy compression data, but it's accurate enough that you can't tell with your eyes. And so that's the idea behind a probabilistic data structure, is it's a little bit lossy enough. A lot of probabilistic data structures can be thought of as sets, peculiar sets, set theory. Right? So, a set where you remove and get the intersections and the unions and that sort of stuff. I'm going to bring my mic here a little closer too and see if that might help with the audio. So, we'll do an abbreviated version of the talk. Sorry about that. For whatever reason, my internet just decided to not be good enough. So, I was talking about probabilistic data structures and how a lot of them can be thought of as unusual sets. Sets in the idea of set theory. So, adding and removing to those sets, getting unions and intersections, the whole Venn diagram thing. And but they're versions of sets that have limited capabilities. So perhaps you can get things from them, but you can't remove anything, or you can get the cardinality of that set, but you can't you can't change its contents other than to add things to it. That sort of thing. One particular variety of a probabilistic data structure will look at membership. So this is an existence. It is a thing in a set. This is that username example I talked about earlier. Is this thing in the set? Yes or no? I can add things to it. I can ask if things are in it, and it will say yay or nay. I can't remove them necessarily. I can't count them. I just know whether it's in there or not. Another one would be cardinality. Cardinality measures how many unique items are in a set. So I've added a star, a square, a circle, and a triangle to the set. And then I can say, well, how many unique items are in the set? There are 4 unique items in this set. Cardinality is just counting the number of unique items. Another one would be getting the frequency of things in a set. A frequency is similar to cardinality in that it's counting, but it's not counting the unique things in the set. It's counting the total number of things in the set per unique thing. So instead of saying, how many things, there's 4 because there's a triangle, a circle, a star, and a square. Here we're saying there are 5 stars, there are 4 squares, there are 6 circles, there are 3 triangles. If we asked how many pentagons were in here, it would come back as none. It would come back as 0 because there aren't any. And so, and this was to count the frequency of these things without necessarily knowing perhaps, the cardinality. Now, maybe. Cardinality you'd probably be able to get, but this is one thing you want to focus on, one type of probabilistic data structure. There's ranking, which doesn't necessarily show you the frequency, but does show you the relative order. So we don't know how many circles there are, but we know that there are more circles than there are stars than there are squares. And another thing we can do with these peculiar sets that are probabilistic data structures is we can compare them. We can get similarity between them. Is this set like another particular set? So here our first set is got, all 4 of these wonderful shapes that are in the Redis logo. The circle, the square, the triangle, and the star. And we can compare it against the set that doesn't have a circle. How similar are these sets? Or the one that doesn't have the square or the circle. And so probabilistic data structures let us think about sets in these narrow ways. There's a lot of choices for probabilistic data structures. Here's a few that I've highlighted here. Plan was to talk about all the ones that are highlighted in blue. I don't think we're going to be able to get to that, but we'll cover at least Bloom filter, and we'll probably get through Bloom filter at least. We'll see how far we get. But here we've got a list of common ones by membership, or for cardinality, or for frequency, or for rank, or for similarity. The ones with little red daggers next to them are things that we can do within Redis. The others are not part of Redis. And specifically the one with the double dagger, hyperlog log, is part of open source Redis. Just your vanilla, sudo apt-get install Redis, hyperlog log is there. The Bloom filter, the Cuckoo filter, the count-min sketch, and the heavy keeper are available in a module for Redis called Redis Bloom. This is a sort of a plugin that you can add to Redis to expand its capabilities. You can add new data types and new functions and stuff to Redis, including Bloom filters and heavy keepers and min hashes, and actually Cuckoo filters. And so that's what a module is, and this is, Redis Bloom adds those. So let's take a look first at Bloom filters. When I've run into people that have heard of probabilistic data structures, they've usually heard of Bloom filters. They might not have used them. A Bloom filter is a probabilistic data structure that is a set that is all about membership. And you can add things to that set, like say, have I seen this particular UFO sighting or not? And then you can interrogate that set and say, have you seen this thing before? and it will respond with a no, I have definitely not seen this thing, or a probably, I've seen it. So it says no or probably. It doesn't say no or yes, because it's probabilistic. Balloon filters are of a fixed size when you create them. So when you create one up and say, I'm anticipating storing a particular number of items in this balloon filter. And they're very, very fast. All the operations against a balloon filter are O of 1. Things that balloon filters are good for are, well, the username problem I've kind of used a couple times here of, is this username taken or not? That's a great scenario for a balloon filter. You take all your users, you shove them into a balloon filter, and then when someone signs up for a new account, instead of having to select star from table with a billion rows, where username equals foo, you just say, hey, balloon filter, is foo taken? If it says no, then you know for sure it's not taken, and it's safe to use that username. And if the balloon filter says probably, then you just deny them. And maybe that's not actually taken, but then that just means there's never a user with that name, but you can actually perform. It gives you the performance you need. A balloon filter is made up of two main things. There's some hashing functions with their seeds. So here we've got 3 hashing functions. We want more than one. I'm using 3 because it fits conveniently on the screen here, and their corresponding seeds. And again, these aren't cryptographic hashing functions. These are, in my implementation that you can check out after the talk, I used a murmur hash. And so these are going to be used much like they were with a hash table. And the other thing you have is a bit array of a fixed width. So this one's 10 bits wide. You would probably, for a real balloon filter, want to go much larger. And the bit array is kind of like the hash table part. It's the table part. It's the array of the hash table. But instead of storing, linked lists with values in them like we do in a hash table, in the balloon filter, we simply set bits high or low. So the way this works is we're going to add a UFO sighting to the balloon filter. We want to know if we've seen this or not for future. This is a new one. We're going to add it, and then we can check later to see if we've seen it or not. And so we've got here Megatron in the bushes. This is a delightful story of some young guys in Arizona who are they stop at a rest area to do the needful biological functions you need to do on road trips, and they saw some lights behind the mountains, and they heard a weird sound behind the bushes that sounded like Megatron from the Transformers transforming, that sound that he always makes, that all the Transformers made. And they freaked out and took off running, and the lights chased them down the highway and stuff. It's a delightful story. So we want to know if we've seen Megatron in the bushes before. And so, well, we haven't seen it. We're adding it to the balloon filter. So let's add that to the balloon filter. So we take the text of that sighting, we run it through all these hashes, and we get hash numbers. We get these 32-bit numbers or 64-bit numbers, whatever your hashing algorithm spits out. But you get this fingerprint, this integer, uniquely identifying that particular string. We get a set of them because we use different seeds. We take that set of numbers and we modulate it with the width of the balloon filter, just like we did with the hash table. And this will give us indexes, just like we got with the hash table. And instead of putting Megatron in the bushes into the array, we simply set a 1 in all the positions where those indexes match. So here, we add to the balloon filter, and we get 5, 0, and 6. And so here's position 0, there's 5, there's 6. So we set those to a 1. And then if we want to go read from the balloon filter and say, read, we're not really reading, we're checking for existence. We're checking for membership. We can say, is Megatron in the bushes in the balloon filter? And so we take that same string and we run it through it, and we get the same calculations, we get the same indexes, and we look at all the results. We look at all the bits. And if they're all 1, then we've probably seen it. If one of them comes back 0, we've definitely not seen it because this string never came in to set it high. And so that's how we can add to a balloon filter. Let's add something else. Let's add, I seen a UFO when I was about 13 years old. This is another UFO sighting from the data set that I've been using here. Actually, if we go over here, this is the data set here. And so if I've seen a UFO. There it is, right there. I seen a UFO. when I was about 13 years old. The year was about 1970. It was in Columbus, Ohio, actually, which is where I'm at. I seen a UFO when I was about 13 years old. We run that through the hashing functions. We get different indices, but we have one that's the same. The 6 is the same. And you might think this would be a problem, but it's not, because those collisions are mitigated. The impact of the collision is not that great because we have multiple hashes. So here we set 2 and 1 to red. We set those to 1s. Those were 0s before. And here in position 6, it's already a 1, so we don't have to change it. But there's overlap, but there's not perfect collision. And so we can ask if I've seen this before, and when we read it, we get all 1s, and we ask about the Megatron in the bushes, and we get all 1s, and everything still works. These hashing functions, since we have multiple hashing functions, it reduces the impact of those collisions. It does mean our bit array needs to be wider, but it mitigates the collisions. So that's a trade-off that you make when you're putting together a bloom filter. However, as bloom filters start to fill up, and eventually all these 0s will get flipped to 1, and you start getting collisions. Eventually they'll fill up completely, and you'll just get false positives all the time. And so here we've added another UFO sighting. Investigators from the Bigfoot Field Researchers Organization observing a glowing green-blue sphere. And when we hash this out and modules it with the width of the bit array, we end up getting numbers that have all collided. So 0, 1, and 6 have all already been set to 1. And so if we had queried this before adding this, it would have been a false positive. But if we queried it after adding it, it wouldn't have been. But this is what happens when you have a complete collision. And it's not colliding with an exact example from earlier. It's colliding with an intersection of the 2 previous examples. So the bloom filter with that total collision starts filling up, and all these are 1s. And when you get into that situation, it just starts returning false positives all the time. So when you're allocating your bloom filters, you need to make sure you make them wide enough with the appropriate number of hashes. How do we figure that out? Well, with this easy math. There's actually an online bloom filter calculator you can use to say how wide should I make it and how many hashing functions should I use. But this math actually isn't that hard. The way to do it manually is you just you get your number of items n, and number of bits or n, number of bits is m, and so you can pick 2 numbers. You know the number of items you want to store. Like I want to store 1 million items in this bloom filter, and you make a guess at how many bits you want to use. And then using those 2 values, you can use the second formula here and solve for k. Once you have k, then you can solve up here for p, and then look at the false positive rate that you're going to get with that number of items, with that number of bits, with that number of hashes. If that's acceptable, then you've solved the problem. If not, you just adjust your numbers and try again. So not that terrible. Bloom filters are kind of cool. Actually, they're pretty easy to code up, but they're also available on Redis. And so if you wanted to use a bloom filter in Redis, you just call BF reserve, give it a key name, give it your false positive rate, and how many items you anticipate having in it. Once you've reserved that, then you can start adding things to it. So you call BF add to add, to that key a particular item, another item, and you got multiple add mad, which lets you add multiple things. What's interesting here is that we add disk to the bloom filter, returns 1. And that 1 is saying we've modified the state of the bloom filter. Here we've added light. That wasn't in the bloom filter before either, and so again we get a 1 saying the bloom filter was modified. However, down here we're adding light a second time. Adding light again is not going to change any 1s, any 0s to 1 in that bloom filter, and so it returns a 0 to let us know that the bloom filter didn't change. And but teardrop was not seen, and so that did change it. And then to use a bloom filter, we call bf.exists with on that key, and we just give it the value we want to see if it's in the bloom filter or not. And there's a multiple exists as well here for light and triangle. I'm going to go ahead and demo this really quick. I've got a instance of Redis running right here from a Docker image. Got the CLI running, and if we go out here to key star, you can see I've got a couple keys out there. Let's create a bloom filter with bf.reserve, and we'll call it just bloom filter. and we want to have 0.005, and let's store 1,000 items in it. So now I've got, if I do a key star, we see it's created that bloom filter right there. I'm going to make this a little bit bigger here, just so you can see it really well. There we go. Now, if I want to do a, BF exists, bloom filter, this is going to return 0 because I haven't put anything in the bloom filter yet, right? No matter what I put in there, it's going to be 0. Let's go ahead and add something to it. We'll do a mad. We'll add in foo and bar, and that both returned 1s. If I add it again, it returns 0s. And if I call exist, like this, foo is going to return 1, bar is going to return 1, baz, which we have not added, returns 0. So that's a bloom filter. They're actually very easy to use in Redis. And there's some libraries to make this even easier. I've got, I think, about 5 minutes left. So I'm gonna skip towards the end here. And I'm gonna skip min hash. I don't have time to go into that. And we're gonna look at top K. So top K is another probabilistic data structure that's available in Redis. We call it a heavy keeper. We call it top K, but it's actually a heavy keeper paired with a min heap. What top K does is it ranks the top K items. And so if you want the top 10 most clickbaity articles of all time, that sort of ranking. The idea here is that you can keep adding the same values to it, and it starts counting them. And we'll give you the frequency. It'll give you the ranking of the top 5 or 10 or however many items you want. Which ones are most commonly seen. You can use this for things like monitoring network traffic to find out, which IP addresses are hitting my website the most. You can use this to do statistical analysis on documents by, saying how frequent are the words by basically counting them, and things like that. And so top K is made up of, like I said, 2 things here: a min heap, which is the thing you ask when you want the rank. The min keeps track of your top K items. And the heavy keeper is busy counting everything. Heavy keepers' counts aren't very reliable. If you ask, you can get the count, but it tends to be less than the actual count. But the ranking is reliable and accurate. Heavy keeper, much like a hash table and a bloom filter, is taking advantage of hashes. We've got over here on the left, we've got a bunch of hash functions, and associated with each of those hash functions is an array, and the array is a fixed width number of buckets. The buckets have in them, each value in them has a count, which starts out as 0, and it has a hash value of the thing, the value that was hashed. A brand new heavy keeper has all of these set to nulls and zeros. In this heavy keeper, when we go to add a value, we're going to add shapes of UFOs, or commonly seen words in UFO sightings. And so here we're going to add the word object. When we add the word object to the heavy keeper, we hash it, we get unique signatures, we modulus it by the width, just like with the bloom filter, just like with the hash table. And then we look in the bucket that corresponds to that index for each hashing function. So we've got one here, number 2 is going to correspond over here. Number 1 is going to be in this position, number 2 is going to be in this position. And what we do is we look in those values and say, is the hash populated? If it's null, then we're good. If it's not null, we say, is it ours or not? If it is ours, then we increment the count. So here they're all null. We add this value. We find all these locations are empty, and so we just set the 0 to a 1. If we go ahead and add the word object to it a second time, it's going to, again, hash the word object, get the indices, look in here, and it's going to say, oh, there's a hash number here already. Let me look at it and see if it's the same as my hash number. Oh, it is the same as my hash number. So we're going to increment the count by 1. And so this makes it heavier, right? As these things become heavy, as the count increases, they become heavier. If we want to query this count, then what we do is we just do sort of the opposite, much like the bloom filter. We take the word object and we hash it, and we got here, and and say, we get all the counts where the hashes match, and we take the largest value out of all of them. In this case, they're all 2 because there's nothing else in this heavy keeper. But and so it's 2. If we want to add a different value, we get the interesting problem of having a collision. So here we've got the word light coming in, and we run it through the hash and get position 1. It's null, that's fine. Position 2 is null, that's fine. But here on the 3rd row, we get a collision. Something's there already. And so that means in that scenario, when we're adding, this 2, this count, has a chance to be reduced. It won't go away, it won't be changed, but the hash will stay the same, but it'll be reduced. If it gets reduced all the way to 0, it's deleted and replaced. And so this is the way that lighter things get eroded and heavier things stick around. And the probability is based off of this formula right here. It's where B, the probability of decay is B, which is a number that's around 1, but bigger than 1, to the negative of the count. And so if there's a big thing, this is going to drive that number way down. If there's not very many, if the count is small, the number is going to be higher. Our math shows a 90% likelihood of decay, and so we decay that value. This 1442 is now a 1 for the object, but it's still there. It's been decayed. And so now if we query the word light, then we find that you get 1, 1, and nothing. And 1, we take the largest, it's great. Object, we take the largest. We find this one's a 1. It's still there, it still matches, but it's smaller. But these are still both 2, and so it's accurately reflecting the count of what was added. Every time we go through this process, we update our min heap and resort it so that the things that have the largest numbers are always in the heap, and then we ask for the top K. That's how we get it. Doing this from Redis is pretty easy. I'm not going to demo this because I don't have time. We call top k.reserve to set up a top K structure. Here we got UFO shapes with how many the top number of things we want. Do we want 3 items that we're going to keep track of, or 10 or 1,000 or whatever? We give it a width, that's how wide that array is that we were modifying. We give it a depth, which is the number of hashes that we want to use. And we give it a decay rate here. It's 0.9. This is the reciprocal of the number that I showed you earlier. And so that sets up a top K structure. To use it, the commands are very straightforward. We call top k.add, and then the key name that we want for the top K structure we've defined, and then the items we want to add. So here we've added disk and teardrop, light, disk, and teardrop. And so if we're counting here, we've added disk 3 times, teardrop twice, and light once. If we ask for the top k.query, we can say, is disk in the top K? It'll say yes or no. What's the count of teardrop? It will return 2. And give me a list of all the things that are in the top K, and it will give us a list of those top K items. So that's sort of top K in a nutshell. I've got a quick demo. I don't think I have time for demo. I probably should take a question or two. But I do have a fun little demo that if you want to check it out later, the code is out there on GitHub, where I probably have time to run it. Let's see here. Yeah. There we go. I've got a little demo here that just does this in Python. I've got a little thing that is going to read that CSV file, a little app that runs. So this little CSV file, it's going out and reading this CSV file and shoving these into a top K structure, parsing out all the individual words for all the UFO sightings in the 112,092 of them I have. And then these go into this little app here, which is running. You can see it's updating about every second or so. And we're finding our top UFO words and our top UFO shapes. So this is using a top K structure behind the scenes to do that. So super quick demo, apologies. Technical problems and all that. So if you want to learn more about probabilistic data structures, this Bloom filters by example article is fantastic. It gives you a nice visual representation of Bloom filters. Here's the calculator I talked about. We have a tutorial on minhash, which I didn't have a chance to talk about, but this is probably the best article I could find on how minhashes work. Here is the white paper on how HeavyKeeper works, which I covered kind of quickly. We've got a UFO sightings data set here, if you want to play with that UFO sightings data set. And newfork.org has is the source of that, the original source of that data. If you want to play with some of these bloom filters in Redis, go out to redisbloom.io. And here is a blog post on Redis from my friend Ariel Stuhl, who worked on the top K for the team. I'm at Redis. We got a Discord server. You should go check it out. We got a YouTube channel. I'm on there talking about things like this. And we got free classes if you want to learn more about Redis. And we got code and slides if you want to check out these slides. You want to learn about minhash because I lost that with technical difficulties. Scan this QR code. It will take you there. The QR code is reliable. It will never give you up nor let you down or take you to some site it's not supposed to. And yeah, that's pretty much all I got. My name is Guy Royse, and again, apologies for the technical difficulties. Thanks.
Okay, thank you. Thank you so much, Guy. Thank you once again for supporting Devoxx Ukraine this year and connecting to us on your Saturday morning. I encourage you and our participants to continue the discussion in the Q&A. So you can join the Q&A discussion through the Rocket platform. So please, dear participants, if you have any questions to Guy, just switch to Q&A and continue live discussions.
Yeah,
so,
I'll be there.
Yeah, thank you once again and have a great day ahead.
Thank you. Have a good weekend.
Thank you. Same to you.